Alrighty, hi guys. So this is kind of just a little explanation video for this week. I've noticed a lot of people seem to be struggling with this. So um, here's an instruction video. I put together this little simulator. I'm sorry this is coming on a little late in the week. It's been a crazy week for me. I put together a little simulator and you'll find it attached to the email. So I sent you this Excel document. And with it, you should be able to, the goal is to be able to toy around with this Lac Operon and see what happens if I do this, what happens if I do that, what happens if I do that. It allows you to put in and take out any of the pieces and see what happens with transcription. So I'll walk you through kind of the basic idea. This is sort of like a little instructions video, and then I'll let you toy around with it. With this, you should be able to understand the homework and, heck, even work it out, do it visually. Because with this, if you know all the right buttons to push, you can get all of the right answers. And hopefully having something interactive and visual will be able to help you understand it better. So let's see if this works. All right. So I've set it up so that it's the Lac Operon. Let me put it back to the basic here. Okay, here we go. We're on basic, and when I send it to you, it'll be on basic. You can do your entire homework on the basic level, and that's why I created it, so that you only get the additional variables to help you understand the rest of the week. So start on basic, make sure you understand basic, and then we'll add in the additional variables. So we've got three things. These are the three that you've included in problem one. The RNA polymerase, the repressor, and the lactose. Now across the bottom here, we have the DNA strand with all the components. We've got the promoter right here. We have the operator over here, and these are the three genes, LAC-Z, LAC-Y, and LAC-A. Now, the whole point of an operon is one promoter for a collection of genes. You might think of it like a light bulb circuit. That's the example I've been using all week. In humans, we don't have operons. So we've wired our house to have one light switch for every light bulb in the house. Because the whole point is we want to control when the lights are on and when the lights are off. I don't want to waste, my electricity bill would be absolutely nuts if I left my lights on in every room in the house all day long, every day. That would get really expensive really quick. And bacteria, it's the same way. I don't want to leave all of my genes on all the time because it's energetically expensive to build enzymes, to build proteins. So I want to control when I make them and when I don't, so that I only make them when I need them. So that's the whole point of an operon. Now, with humans, we don't have operons because, like I said, we have one light switch for every light bulb. Bacteria like to be efficient. Bacteria have realized that some jobs in the cell require more than one protein, more than one enzyme to finish the job. You might think of it like construction workers. If you're going to build a house, you don't just call the construction workers. You need electricians and plumbers and surveyors and all sorts of people. So we have to pick up the phone and call each one individually. The bacteria are like, why bother? Why not just call a company that has all of them? And then I can activate them all with one phone call. With my light bulb example, we've got more than one light bulb on the same circuit. So if I flip the switch on, I'm going to turn on 3 light bulbs instead of 1, because I need all 3 of them to light the room up adequately, rather than flipping on 3 light switches to turn on 3 light bulbs like you have to do in humans. So that's what an operon is. It's one light switch for more than one light bulb. Or in this case, the enhancer, the operator, and the promoter, these guys are the light switch. And we're coming out with 3 different enzymes in the end. We're going to transcribe and then translate these into enzymes that are going to do the job of, in this case, digesting the sugar lactose. So lactose is a sugar. the sugar lactose. The sugar lactose. So the sugar lactose, this is what it looks like. It looks kind of crazy. For those of you who haven't taken chemistry, don't worry about it. But I just wanted to show you that the body is not designed to digest lactose. It's designed to digest glucose. Glucose, it's able to break it down and get energy out of it, but lactose, it doesn't know what to do with that. It can't use it. So we have to have some enzymes involved, because it turns out lactose is actually a combination of sugars. This is glucose over here, this little hexagon with all the weird sticky outy things on the left is glucose, and over here on the right we have another sugar called galactose, which can be converted easily into glucose. But glued together, I can't use them. So I need someone that's able to go and cut them apart. See how they're kind of glued together there in the middle? I need someone to be able to come in here and cut them apart so that they're two separate molecules like this. So this is the glucose over here, and that's galactose, which I can turn into glucose. And now I can use that because this is glucose, and I'm designed to handle glucose. So then I go and eat that for energy, but the cell can't use them when they're glued together. So the point of the Lac Operon is to make enzymes that are able to come in here and cut them apart so that they're not holding hands anymore. So these three the enzymes made by these three genes over here, LAC-Z, LAC-Y, and LAC-A, those are necessary for cutting the two sugars apart so that other enzymes in other parts of the cell can use it for energy. And that's really important, especially if I don't have glucose present. And that becomes important later. Okay, so for this part of your homework, the way this thing works, so you've got the operon, and I'll show you there is a selection there. We're on the level basic. There is a little pull down tab there too, but for now just leave it on basic. And then we've got buttons here. The red is like a light, you might say. It indicates whether it's there or not. So if I want to add that particular component in, all I have to do is press the plus button, and it'll add it in. See, I have a green light now, so RNA polymerase, boom, there it is, it's on the promoter. Because RNA polymerase hops on at the promoter. If I want to add a repressor, then I press the plus button on that one, it gets a green light, and boom, there's my repressor on the operator. If I want to add lactose, then I just press it and get a green light. There's lactose. It's out there. It's floating around in the environment. Now, I ask you to pause here and predict what will happen. Because see, the point here is this is how we turn it on and off. The repressor sits on the operator, and it's just a big protein, and it chills there. It binds to the DNA and just chills there. Now notice the operator is between the promoter and the genes. Now, RNA polymerase just hops on at the promoter and it's designed to go. It just goes. But if the repressor's in the way, let me take away lactose here for a sec. If the repressor's in the way, boom, RNA polymerase is just going to run into it and not get to the genes. So no matter how many times he hops on the promoter and goes, as long as the repressor's there, the genes don't get transcribed. And what we mean by that is activated. When on the homework where it asks you if it's activated or repressed, what we mean by activated or repressed is whether or not transcription happens. Whether or not RNA polymerase is physically able to get to the genes and transcribe them into enzymes. Well, into mRNA, which turns into enzymes, but I'm just abbreviating it here. In this case, if you just have RNA polymerase in the repressor is smack in the middle of the road here, and our RNA polymerase is just going to run into it and fall off. So he can't get down here to do transcription. So in this case, it would be repressed because the repressor got in the way. That makes sense so far? But now, if I press reset, so go was how we ran it. So you add the pieces and then you press go and it shows you what will happen. Now I can press reset and it'll reset it back to blank. So then I can go in and add other pieces. If I have RNA polymerase, the repressor, and lactose, what do you suppose will happen? Well, lactose is what we call an inducer. An inducer, if you think about like pregnancy, if they induce you into labor, they are causing labor to happen. So an inducer is any outside factor that is causing transcription to happen in one way or another. In the case with lactose, it's an inducer because it causes transcription to happen because it binds to the repressor, causes the repressor to let go of the DNA and float away. If the repressor is no longer in the way, RNA polymerase won't run into it and it'll be able to get down here. So if I press go, boom, there it goes. So the repressor got dragged off by the lactose. RNA polymerase was able to travel down the tracks here, and it transcribed Lac Z, Lac Y, and Lac A, and eventually they got made into proteins, beta-galactosidase, lactose permease, and transacetylase. You don't necessarily need to know those, but I put them in there. And these three enzymes are able to go destroy lactose. Now, let's pause here for a sec, because this system is only good if you can turn it back off again. Well, how do you turn it back off? What did we say these three enzymes do? They digest lactose. They turn lactose into glucose. Glucose doesn't bind to a receptor, only lactose, or a repressor, sorry, only lactose does. So these guys will actually go and eat lactose. They'll destroy the lactose, and if the lactose isn't there anymore, what happens? So if I want to take it away without having to reset the whole thing, I can come over here and press a minus button, and that takes it away, and now it will change what happened, because if the lactose goes away, because it was going, because RNA polymerase travels to the end, if I put lactose back here, RNA polymerase travels to the end, and then it always hops back off, hops back on the promoter and goes. Technically, like lots of RNA polymerases are going on this. It's like a conga line. So the first guy goes, and then the next guy hops on and goes after him, but you can just picture it as it's recycling. So it's going to keep going until a repressor gets in the way. And so these guys will be out here, and they'll destroy lactose, and they'll chew on lactose until there is no more lactose. And then if there's no more lactose, I don't need to make any more of these things because their whole job is to get rid of lactose. So if it's gone, then lactose vanishes, and when the guys come back around to do it again, they'll run into the repressor, and I've turned it off effectively. And I mean, the enzymes will disappear because we're constantly destroying proteins and remaking them. So the enzymes will disappear and the effect will be gone, and I won't waste any more energy building more. So you can play around with this, and all that first problem of the homework is saying, well, if I turn on these two pieces and turn off that one, what will happen? If I turn on these two pieces and turn off that one, what will happen? If I turn on just this one piece and not the other two, what will happen? And it's all, so play around with this, but what I ask you guys to do is I design this thing not to give you the answers. I design this thing to be a visual for you so you can picture what's going on. So why I didn't make it automatically happen is so that you can put in the pieces and be like, well, if just RNA polymerase is there and there isn't a repressor in the way, what will happen? If I have just RNA polymerase and lactose, you know, what's going to happen? It allows you to visualize, if I've got these pieces, now physically, will RNA polymerase be able to get there? And then you can press go and see what will happen. Does that make sense? So if I have RNA polymerase and lactose, and I'm sorry it's glitching, I'll go in there and fix that before I send it to you. But it should be able, you'll be able to go and put those pieces in, and it'll work just perfectly. And it'll be able to walk you through it, and you can basically check your answers. If it's activated, if you end up with the enzymes in the end, and it's repressed if you don't.